Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we structure weird and wonderful science directly into your neurons. I'm Ian Woolf. On this edition, Alison Campbell puts quantum dots under the microscope. But first up, here's news of nuclear contamination. Radiation whoopsies? On the 21st of June 2019, less than 2 weeks since the Australian Nuclear Science and Technology Organisation regained a licence to produce nuclear medicines, 3 workers at the facility in Lucas Heights handling molybdenum-99 were exposed to unsafe levels of radiation. 2 of the workers were estimated to have suffered in 1 day unsafe radiation exposure equal to about 3 times a year's safe dose limit. The Australian Radiation Protection and Nuclear Safety Agency, ARPANSA, will note the incident as Level 2 under the International Nuclear Radiological Event Scale, when the amount of radiation exposure is formally confirmed after investigation. The scale ranges from no safety significance at 0 to a major incident at 7. Molybdenum-99 is used to diagnose a variety of heart, lung, organ and musculoskeletal conditions. The Australian Radiation Protection and Nuclear Safety Agency has told the Australian Science, Nuclear and Technology Organisation that they cannot continue to make molybdenum-99 until they provide an assessment of what happened, why it happened and how they will prevent it from reoccurring. This report is due on Friday, the 5th of July. In March 2019, 3 Australian Nuclear Science Technology Organisation workers were exposed in a chemical spill. Sodium hydroxide spilled onto the faces and arms of the workers from a burst pipe, causing severe burns. In 2017, a worker was contaminated through 2 layers of gloves from a spilled vial of molybdenum-99. He was left with blisters on his hands and a higher risk of developing cancer. The 2017 incident was graded by the Australian Radiation Protection and Nuclear Safety Agency as a Level 3 incident. In their report, they said the worker had been exposed to 40 times a year's safe dose limit to the skin. They also found that the Australian Nuclear Science Technology Organisation had been in breach of the Australian Radiation Protection and Nuclear Safety Act. An independent review of the Australian Nuclear Science Technology Organisation's facility at Lucas Heights in October 2018 found that it failed modern nuclear safety standards and should be replaced. In the same week that review came out in 2018, the Australian Nuclear Science Technology Organisation confirmed that another 5 workers had received a dose of radiation, which they downplayed as less than a chest X-ray. Meanwhile, the Australian government has raised the idea in the media that Australia should change the law to allow nuclear power plants. What could possibly go wrong? You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Quantum dots are used in newer TVs, but what are they? Alison Campbell is studying nanotechnology at the University of Sydney and is completing her honours year in chemistry with research into quantum dots. I began by asking her, What is a quantum dot?
Well, it's a very fancy word, but what it means is a very, very tiny little sphere which is made up of different metals or semi-metals from the periodic table, which make it a semiconductor. So that means that it's not quite metal, which is good at conducting electricity. It's not quite an insulator, which is not good at all. It's halfway in between. And these semiconductors are what we find in our phones, in our TVs, in our electronics. So it's that same material, but a very, very tiny amount of it.
And when it's so small, it has different properties to regular size semiconductor molecules and devices.
That's exactly right. Things get a bit weird when we take it down to the nanoscale, when we look at nanotechnology. In fact, when you think about light, you can think of a wave that goes up and down, and if you have a very small area for that wave to go up and down in between, it gets a bit trapped, and so that makes for really interesting phenomena. For example, these quantum dots that I look at, they can absorb light and emit light. So if I'm looking at a vial of them, there'll be a really interesting colour. And that will lead us to some great applications for them.
How do you control what they do?
So you can control the colour of light that a quantum dot emits based on its size, because at the end of the day, each colour can be defined by a particular wavelength. So if you have a large wave that kind of goes at an easy peasy pace, up and down, that might be a red colour, whereas if you have an energetic wave that's up and down all the time, that might be a blue colour. So if you have a larger quantum dot, that will look red, and a smaller quantum dot will look blue. And this is really cool because we can make a colour that we want based on the size of the nanoparticles that we're actually looking at, the quantum dots.
And does that work for absorbing light as well?
Yes, the absorption spectrum changes with size as well in the same manner. So that's a really interesting property as well, one that I'm quite interested in, and that's what I'm studying.
So they can absorb light and they can emit light, and the frequency depends on the size. Can you control when they emit light based on other things?
Yes, so when you look at a quantum dot by itself, one at a time, you can see some really interesting things, like the fact that it will emit light for a little while and then it might stop and it will look dark, and then it might come back on and emit light again, like someone standing at a light switch and flicking it on all the time, which is quite annoying for whoever is in that room. So when you look at a quantum dot on the nanoscale by itself, you can see that, and we call that fluorescence blinking. So you can observe it coming on and off, but at the moment we can't control that. We can only control the frequency with which it does that, whether it does it at all, if it does it quite a lot or not much. And we want to try to make better quantum dots for applications where they don't blink. And so we're thinking about ways that you can engineer quantum dots to not blink. But other than that, we couldn't say, okay, stop blinking now, come back on. That's something that we can't control as of yet.
And do we know why they're blinking when we're not stimulating them?
So to get a quantum dot to blink, you need to give it laser power. You need to provide energy. A way that you can think about this is like if you have a ladder on the side of a building, and giving a quantum dot energy will make it climb up that ladder, and when it climbs back down again, you can see it's giving out the extra energy in the form of light. But sometimes something will happen where the quantum dot no longer gives out that energy as light. It's still getting the energy from the laser, but the energy is being dissipated in another way. So maybe in our building with a ladder picture, the quantum dot might climb the ladder, the laser is still going to make it climb the ladder, but then it might climb inside a window and come down the stairs on the inside, and we can't see that anymore, and that's why it looks dark for that period of time.
Right, and so what sort of uses can you put to blinking quantum dots?
Well, we are excited about quantum dots as an academic group because they have great application potential. For example, we could use them in single molecule biological sensing. You could put them inside the body when you do a PET scan or a CAT scan. These are just ideas that as a science community we have. However, the problem is when they blink, you can't see and track where they're going through the body. It might, be bright when it's over here and then it goes dark and it pops up again somewhere else. Is that the same one? Is that a different one? We don't know. So we want to make them stop blinking for that. Another application is in lasers. So we use light as a society quite a lot for industry and for research purposes. And so if we can get quantum dots to be reliably emitting single photons, that would be a great application in lasers. And there's a third application. We can use them in TV display technology. So at the moment, we have semiconducting materials in our TVs as well. But if we can get quantum dots into our TV display technology, we can control the colour, like I mentioned before, and we can have a better resolution and a better pixel density by having single photon emitters in our display. In fact, Samsung has made a prototype already. I'm not quite sure how they manage that, given that we know blinking is an issue. And so if we want to have a good TV display, we don't want it to shimmer every now and then and miss particular parts of the picture of whatever movie we're watching. That's another reason why we should stop blinking, to make that better.
And on the absorption side, can they be used for solar cells?
Yes, that is something that our group is interested in as well. We're interested in solar cells based on quantum dot technology. Also, organic solar cells is something that people in my group are working with. So we are looking at ways that we can make solar cells cheaper and more efficient, which is obviously going to be of great benefit to society, given that fossil fuels will run out eventually and we would like to have an alternative. And at the moment, organic solar cells are very cheap compared to normal solar cells. So that is something that our group is quite interested in, clean energy. And another thing that we work on is organic solar cells, which use molecules that resemble chlorophyll to also produce electricity, which we can use for our day-to-day purposes.
And can you also use the quantum dots to either absorb or emit light up into the X-rays or down into infrared?
You can create a quantum dot to emit in the infrared range, the near infrared range, and you can create quantum dots that might emit in the UV range possibly, but I know that it becomes a lot harder and they get a lot less stable when you try to make them smaller, and there's a fundamental limit to how small you can make them. So I'm not sure that we can get as good as X-ray emitting. I think that might be a bit optimistic, but we can certainly manipulate the output wavelength more or less in the visible spectrum and maybe a little bit more on either side if you're lucky.
Are there medical uses?
So as I mentioned before, one way that we can use quantum dots is to do biological sensing. If we want to have a look at particular biological processes, or if we want to track movement of particles through the body, that's a great application for quantum dots. And given that my expertise is in physics and chemistry, I'll leave that to someone else to be the person to implement that. But it is really great that we can work together as a scientific community and everyone can bring their expertise and create this long chain of people that can take a technology and make it useful to someone else. And we work together to do that across disciplines.
So your project very specifically is trying to get them not to blink?
So my project is in single molecule spectroscopy. I'm taking these quantum dots and I'm looking at them one by one. And the big goal is to create a better engineered quantum dot for the purposes that we want to use it in. So as I mentioned before, if we want to use it in biological sensing and TV displays, lasers, we don't want them to blink. I think that is something that we will be working on as a scientific community together rather than myself only to try to get them to stop blinking. So at the moment what I'm focusing on is just looking at different sizes and different structures, different geometries to see what works best and recommend where we can go in the future in terms of building the ideal quantum dot. So my project is looking at the way that they blink, how long they spend in the on state, the off state, how quickly they swap, and that will inform where we go in the future.
And what brought you to this field?
So ever since I was young, I've always liked to ask why. I was that annoying kid the whole way through high school, which made my teachers scratch their head. So I really like asking, why is it that something does what it does? That led me to the University of Sydney to study science, where I majored in physics and chemistry. And for my honours year, I had the opportunity to choose physical chemistry, which is basically halfway in between. And that was a happy medium place for me to be. And so it's great that I've found myself in this environment where I can use both my physics and my chemistry knowledge and be supported by a great research group and whole school as well.
How is it you're able to see single quantum dots?
Well, there's quite a process to go through to make sure that you can see them one by one. We start with a solution of a fair amount of quantum dots, which might look like a coloured vial if you want to have an image in your head. I take that coloured vial and I dilute it down quite a number of times. So I'll do a 10 times dilution, maybe 5 or 6 times, which is quite a lot of a dilution to do. And we get into nanomolar concentration ranges. And so from that, I spin coat this solution onto a cleaned glass slide. So that means I take an amount of the solution and I drop it on while the slide is spinning, and it spins off all the excess, and what's left behind is a small number of quantum dots. I then put a second glass slide on top and use this sticky stuff called epoxy resin around the edge, and that keeps out the oxygen. It means that no oxygen can get in, because that is a problem in terms of looking at quantum dots. That's an important thing. And once I've got that, I can mount it on another piece of glass and take it to the microscopes, where I use a wide field microscope, which means I can see an area that's about 50 by 50 micrometers all at once. There are other microscopes where you can only see a little pinprick at once, but I'm using one that I can see a whole range. And then I can find my sample, which is kind of like finding a particular layer in a hamburger. So if you have a hamburger and all you want to look at is the lettuce, you have to move the hamburger up and down. In the case of the microscopes, you actually keep the sample still and you move the objective, which is where the light is collected, up and down until you can see that lettuce layer, and then the quantum dots will look like stars in the night sky. It's really beautiful and it makes me excited every time.
How can you change the properties of the quantum dots to try and make them blink less?
So you can wrap a protective shell around the outside. That's one strategy. In fact, what I'm doing at the moment is I'm comparing quantum dots that are the naked core, which is like a sphere of cadmium selenide crystal. I haven't personally wrapped it, but we've bought the quantum dots from someone else who has wrapped a layer around the outside of cadmium sulfide and then another layer of zinc sulfide. And so that makes a gradient going outwards, which protects the inner core, which is where all the exciting stuff is happening, where all the light is being emitted from. And the idea is that it protects the core from any surface passivation, which means ways that the light can be distracted away from reaching the objective.
Can you absorb and emit wavelengths other than visible light with quantum dots?
Well, I know that if you make your quantum dot quite large, there's a possibility to be absorbing and emitting in the near infrared range, which is the very, very red end of the visible spectrum. And I suspect that if you go larger, you can possibly absorb and emit even longer wavelengths. However, at some point it'll become more like a bulk material, and then you'll see these quantum effects disappear. And I'm not quite sure where that point is, but that will be a point that will arise eventually. In the other direction, going to shorter wavelengths, I know that the shorter wavelength quantum dots can be quite unstable, and I know that there has been quite a difficulty to synthesize and study those quantum dots. In fact, from my range, the smallest size, which is the smallest wavelength emitter, is the most problematic one, and I always need to centrifuge it, which means that part of the solution which clumps together will fall to the bottom, and it's aggregating because it's unstable compared to the others. So it is a bit problematic, and I'm not sure how far you could go before it would be too problematic at all, but I suspect that it wouldn't be possible to do a quantum dot anywhere past the UV area of the visible spectrum. And also you need to remember that as you're going smaller, you're getting less and less atoms, and at some point you'll have no atoms at all. So that's obviously a fundamental limit.
I've read some people compare quantum dots to artificial atoms. What does that mean?
Well, it's funny because I think how you think of a quantum dot depends on your background and what science you've studied and what you've been exposed to. Because if you're a chemist, you can think of a quantum dot as one big molecule with a bulk crystal structure, perhaps. If you're a physicist, you might think of it as a 3D potential box that confines otherwise free electrons and holes. And so I think your opinion on what a quantum dot is can be quite influenced on where you're coming from. And I think that's why it's really cool that I can combine my chemistry and physics knowledge that I've had in the past to be where I am right now.
Well, isn't a lot of chemistry based on what the free electrons do of adjacent atoms and molecules?
I think in large part chemistry does come from the movement of electrons, and particular the movement of bonds and atoms, and that's all related to each other. So yeah, I think the electron is quite an important fundamental part of chemistry. So an atom is made up of many different things: protons, neutrons and electrons, and a quantum dot is also made up of those things, but only because it's made up of other atoms, obviously. However, I think you can see some resemblance due to the fact that the electrons are confined in a particular space, and that's what makes it quantum and weird. And on the nanoscale, things get different when we get down to there, as I mentioned before. So in some ways, I think it is like an artificial atom if you're not looking at it too closely, perhaps.
So if high school students want a career with quantum dots, what path should they take?
I think that would be really cool if high school students wanted to have a career in quantum dots. Please come and join us is the first thing I'd say. And I think it's a good idea to just keep asking why, wherever you are, whatever you're seeing. I think that builds a good habit of thinking about why things are how they are. Why is the sunset at beautiful colours, and why does my pen drop down to the ground when I drop it? That one's obvious, but anyway, things like this that you can think about why will help you when you're coming into the research sphere to be able to look at something and think, oh, why does it happen like that? And so get involved in your school as much as you can and study science subjects in year 11 and 12 in particular. I know that there's an exciting new subject, which is the science extension subject, and I really wish I had the chance to do that. So if it comes your way, take it up. And depth studies are a good way of really getting into a particular topic and exploring it deeply. So I recommend doing those and getting involved. And yeah, look forward to your university years because it will be a great time. It really is a great atmosphere where you can meet people that are like-minded and study what you're really interested in. So get keen.
If you were to give advice to your younger self about entering this field, what would you say?
I'd say believe in yourself. I think we all have that voice inside our head that tells us our finite limit of what we can do. And I think it's a good idea to remember that you can do anything, just not everything, if you put your mind to it. And I think going through particularly physics with a large male cohort, sometimes it made me feel like I didn't understand things where everyone else did. But there are people out there who will say that they know things when they 90% know them, and there are people out there who will say that they don't know something when they 99% know it. And I'm one of those second type of people. And so if you're like me, I would say just believe in yourself and say what you do know and believe that you know that. And don't be distracted away by the other people that seem to know everything, because there's always so much more to learn and no one knows everything, and that's why we work together as a community in science.
Alison Campbell, thank you very much.
You're welcome, it was a pleasure.
That was Alison Campbell, honours student at the University of Sydney's School of Chemistry, studying quantum dots and how to make them blink only when you want them to. And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker, or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions, and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please like the Diffusion Science Radio page on Facebook and rate us on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. The news music was Rhinos Theme by Kevin MacLeod of Incompetech.com. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including 2 RBM in the Blue Mountains of New South Wales, 8 CCC in Alice Springs and Tennant Creek, 2 MVR in Nambucca Valley, 3 MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, 2XXFM in Canberra, and my local station, 2RDJ in Burwood, New South Wales. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com. And check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 950 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Join my patrons at patreon.com/diffusionradio. Make a donation through paypal.me/Ian Woolf. Subscribe to the Diffusion YouTube channel at youtube.com/c/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.